Bismillahirrahmanirrahim. Assalamu alaikum students. Today we're going to discuss an important topic. The topic is the DEBYE model. DEBYE model of what? DEBYE model of heat capacity of a solid. Let me underline it. DEBYE model for heat capacity of a solid, right? So before going to DEBYE model, I will first refresh your memory about heat capacity, Dulong-Pettit law, and Einstein model of heat capacity of a solid, as we have discussed these things in the previous lectures. You know, heat capacity C is defined as dQ by dt, where dQ is the amount of heat put into the system and delta T is the change in the temperature of the system, right? And if we are talking the amount of the system is taken as 1 mole, then this becomes molar heat capacity, right? So when we have 1 mole of a substance and we talk about delta Q by delta T, where delta Q is the heat required to raise the temperature of that 1 mole of substance by delta T temperature, then C is molar heat capacity of the substance. And we know if the system is placed at constant volume, that means if the process is carried out at constant volume, then we can write CV as dou E by dou T at constant V, where this E is internal energy of the system, right? This thing you know, CV is now what? It is molar heat capacity at constant volume. So we are taking 1 mole of a substance. So if we have internal energy of some system, then if we differentiate that with respect to absolute temperature, treating volume constant, what we get by that derivative, we get molar heat capacity at constant volume if amount of the substance is 1 mole. Now, this heat capacity depends on the temperature in the manner shown in this figure 1. We have already discussed this. I am just refreshing your memory so that you can understand the current topic. So let me draw the figure. Name it figure 1. So curve goes like this. So here the value is 3R. So this figure 1, what does it show? It shows dependence of heat capacity I should write molar heat capacity of solids on temperature. It is dependence of heat capacity, molar heat capacity, more specifically, molar heat capacity at constant volume of solids on temperature. So we are plotting CV versus T. T is absolute temperature in degree Kelvin. CV is molar heat capacity at constant volume. So this is the actual behavior. This is the actual behavior, right? You can see at high temperatures, the value of CV is close to 3R. So at high temperatures, the CV is close to 3R, right? Where R is, as you know, R is universal gas constant, right? And you know R is approximately 2 calories per degree Kelvin mole. So at high temperatures, CV is approximately 6 calorie per degree Kelvin mole, because it's 3 times R, 3 times 2 is 6. So R is 2 calorie per degree Kelvin mole. So at high temperatures, CV is 3R, which is 6 calorie per degree Kelvin mole, right? And you know this range, this high temperature range, let me use another color. This range usually includes room temperature, right? So it includes room temperature usually. Now the fact that CV is nearly equal to 3R at high temperatures, regardless of the substance described, is called, what is this called? It's called Dulong-Pettit law, right? We have discussed it already. Now, the deviation from this law in the low temperature regions, as you can see in the figure, this is 3R, but actual behavior of the heat capacity CV is shown by this curve. So the deviation from this law, Dulong-Pettit law, in the low temperature regions is strikingly demonstrated by figure 1. From figure, as you can see, as T decreases, CV also decreases and vanishes entirely at absolute zero here, right? Another observation which we will be discussing in this lecture or coming lecture is that near absolute zero, CV is proportional to TQ. In this zone, near absolute zero, temperature, we will see experimentally CV is proportional to dq, right? Then to address this issue, the behavior of heat capacity at low temperatures where Dulong-Pettit law fails, we discuss another model, that is Einstein model. In Einstein model, what we did, we said that in Einstein model, the atoms are treated as independent oscillators, but the energy of the oscillator is given by quantum mechanics rather than by the classical result. When we justify Dulong-Pettit law, we derived it from classical result, and in that we assumed the average energy of the harmonic oscillator, one-dimensional oscillator, equaled kT, where k is Boltzmann constant and T is absolute temperature. So this is classical result. I mean, we use a Dickey-Partian theorem, and we then said we can treat the solid as a combination of one-dimensional oscillators, and uh, average energy per oscillator is kT, where k is Boltzmann constant and capital T is absolute temperature. Then we justified CV equal to 3R from that. But in Einstein model, we don't use this expression, this classical result for average energy per oscillator. Instead, we use this h bar omega or e raised power h bar omega over kt minus 1. This was our result for average energy per oscillator in Einstein model. H bar omega over e raised power h bar omega over kt minus 1, where you know h bar is h by 2 pi, h is Planck's constant. Omega is frequency or angular frequency, T is absolute temperature, K is Boltzmann constant, right? And when we use this expression for average energy of an oscillator, then we derived the expression for CV in Einstein model that turned out to be this 3R times h bar omega e over kt square times e raised power h bar omega e over kt all divided by e raised power h bar omega e over kt minus 1 square. This is the expression for CV, that's molar heat capacity at constant volume according to Einstein model. CV equal to 3R times h bar omega e over kt whole square times e raised power h bar omega e by kt over e raised power h bar omega e by kt minus 1 square. So let me name these equations. I name this 1 and this equation second. And we then simplified this equation 2 by introducing Einstein temperature. So equation 2 may be simplified by introducing Einstein temperature theta E, where how we define theta E? K theta E is h bar omega E. K theta E is h bar omega E. So equation 2 becomes, we have already discussed this all in previous lectures. So this equation becomes Cv is equal to 3R times theta E over T square times e raised power theta E over T over e raised power theta E over T minus 1 square. Let me name this. This is my equation 3. Let me check it. Cv is 3R times theta E by T whole square times e raised power theta E by T over e raised power theta E over T minus 1 square. Now, if we plot Cv versus T using this equation, we obtain a curve of the same general shape as in figure. What was our figure? Figure 1. This figure. This figure 1. So I'm saying if we plot Cv versus T using this equation obtained from Einstein's model, we obtain a curve of the same general shape as in figure 1, right? Then what is the issue with Einstein's model, right? And from this equation, we can see qualitatively that theory is in agreement with experiment over the entire temperature range. In particular, if you see from equation 3, Cv approaches 0 as T approaches 0 degree Kelvin. A new and important feature of equation 3, which was lacking in the classical theory, right? Then what is the issue? The issue is, although the fact Cv approaches 0 as T approaches 0 Kelvin agrees with experiment, the manner in which this is approached is not. I repeat, although the fact that Cv approaches 0 as T approaches 0 degree Kelvin agrees with experiment, the manner in which this is approached is not. Cv approaches 0 exponentially, according to equation 3 or Einstein's model, while experiments show that Cv approaches 0 as T cube. Let me write, according to equation 3, which is Einstein model, CV approaches 0 exponentially, while experiments show that CV approaches 0 as TQ, right? That means the decrease predicted by Einstein model is much faster than warranted by experiment, and this is the basic weakness of the Einstein model. So to overcome that weakness, Peter DEBYE gave another model which is called a DEBYE model, which we have to discuss now. So let's move to our DEBYE model. I first justified why DEBYE model is required. So the atoms in the Einstein model were assumed to oscillate independently of each other. Actually, the idea of independence here is not a viable one, because since the atoms do interact with each other, the motion of one atom affects its neighbors. The motion of these in turn affects their neighbors and so forth, so that the motion of one atom anywhere in the solid in fact affects all other atoms present. Thus, we need to consider the motion of the lattice as a whole and not a single independent atom. That is, we must consider the collective lattice modes. Let me encircle it. We must, I'm writing this inverted commas to remember it. We must consider the collective lattice modes, right? The most familiar example of such collective modes is the sound waves in solids. When a sound wave propagates in a solid, the atoms do not oscillate independently. Their motions are orchestrated in such a manner that they all move with the same amplitude and with a fixed phase relationship. Now, using sound waves as a prototype of lattice modes, let me write it using sound waves as a prototype of lattice modes. DEBYE assumed that all these modes have a character similar to sound waves. That is, they obey the same dispersion relation given by omega is VSQ. Let me name it. We have discussed this equation as equation 4. You know, Vs is the velocity of sound, Q is wave number, omega is angular frequency. We will now see that how this may be used to evaluate heat capacity. We need to note that in the DEBYE model, the frequency of the lattice vibration covers a wide range of values, since as Q varies, so does omega, right? This is unlike the Einstein model, in which a single frequency was assumed, right? Now, the lowest frequency in the DEBYE model is omega equal to 0, corresponding to Q equal to 0, or an infinite wavelength, because Q is inversely related with wavelength. The highest allowed frequency is determined by a procedure which we are going to discuss in this lecture now. Now, the assumption that the sound dispersion relation, equation 4, this one, holds for lattice waves is an approximation, in as much as it ignores the discreteness of the lattice. The approximation is expected to hold well for those waves of long wavelength or low frequency where the consequences of discreteness are unimportant. But when the wavelength is short enough to be comparable to interatomic spacing, the DEBYE approximation, equation 4, will certainly break down, right? So now let us calculate heat capacity on the basis of DEBYE model. Now let us calculate heat capacity on the basis of the DEBYE model. Now, in finding the energy of vibration, we note that each mode is equivalent to a single harmonic oscillator whose average energy is therefore given by which equation? This one, right? I repeat, in finding the energy of vibration, we note that each mode is equivalent to a single harmonic oscillator whose average energy is therefore given by equation 1. The total energy of vibration for the entire lattice is now given by. Let me use another page. The total energy of vibration for the entire lattice is given by E is equal to integral G omega d omega. Let me name this. This is my equation 5, right? Why the integration is effected over all the allowed frequencies. You know here G omega is the density of states function, right? And this one is E bar omega or epsilon bar omega is what? Is the average energy of the oscillator or average energy per mode given by equation 1, h bar omega over e raised power h bar omega over kt minus 1, right? And equation 5 follows from noting that g omega d omega, this g omega d omega, is the number of modes in the range omega and omega plus d omega, and the energy of each of these modes is equal to epsilon bar omega, given by equation 1, which I already discussed. So in other words, we are treating the vibration lattice, we are treating the vibrating lattice as a set of collective modes which vibrate independently of each other. So in evaluating this equation 5, we substitute for epsilon bar omega from equation 1, this one, and density of states is substituted from the previous equation. We have discussed that in last lecture. Let me write this density of states is let me write that equation first. It was 3v by 2 pi square omega square by vs cube. Let me, I have written it in chalo. It's my 5. Let me write it here, not here. Let me clear it. So using equation 1, that is this equation, for average energy and G omega equal to 3V by 2 pi square omega square by Vs cube in equation 5 we get this G of omega, density of status function we have derived in the last lecture. It is 3V by 2 pi square omega square by Vs cube, where capital V is the volume of the sample, omega is angular frequency, Vs is the velocity of the wave through the material, velocity of sound. So when we do this in equation 5, we get E equal 3V by 2 pi square Vs cube integral omega square h bar omega by e raised power h bar omega by kt minus 1 d omega. Let me name this. This is my equation 6. Let me encircle it. You can check it. We have simply substituted for average energy from first h bar omega by e raised power h bar omega by kt minus 1. That is this h bar omega by e raised power h bar omega by kt minus 1. And this thing 3v by 2 pi square omega square by vs cube is g of omega. As you can see, 3v by 2 pi square omega square by vs cube. Right? So this is our equation 6, which gives us the total energy of a solid 3v by 2 pi square vs cube omega square h bar omega by e raised power h bar omega by kt minus 1 according to DEBYE model. Now, before we can evaluate the integral in equation 6, we need to know its limits, namely the lower and upper ends of the frequency spectrum. Now, the lower limit is evidently omega equal to 0. This is lower limit, right? The upper cut of frequency was determined by DEBYE by requiring that the total number of modes included must be equal to the number of degrees of freedom for the entire solid. This is important. Lower limit in the integral of equation 6 is omega equals 0. I will write it in red. The upper limit or upper cut off frequency was determined by DEBYE by requiring that the total number of modes included must be equal to the number of degrees of freedom for the entire solid. This is important. Now, since this number, total number of degrees of freedom, is 3Na and is Avogadro's constant, we are taking 1 mole of the solid, so it will contain any number of atoms. 3Na is the total number of degrees of freedom for the entire solid, because each atom has 3 degrees of freedom. So the above condition may be expressed in terms of the density of states as G of omega d omega 0 to omega d equal to 3Na. Let me name this equation. This is equation 7. Let me encircle it. This equation is simply saying mathematically that the total number of modes included in the DEBYE model is equal to number of degrees of freedom for the entire solid, where this cutoff frequency denoted by omega d is called DEBYE frequency. This is called DEBYE frequency, right? We'll draw a figure. We have given one figure, so we'll draw another figure. Figure 2 shows, we'll draw that, shows graphically the manner in which this cutoff is accomplished. You draw this figure so you know how density of states function varies with omega. As you can see this from this expression, it is proportional to omega square. We have already drawn this figure in last lecture. So it's like this. So what Peter DEBYE did, he limited the upper frequency possible by omega d This is my figure 2. This shaded area under this curve is what? It is simply, this shaded area is simply number of modes, which is this integral. And this number of modes, Peter DEBYE, equated with 3Na, right? So let us move. Now the DEBYE frequency, can be determined by substituting for G of omega, that is G of omega, this expression, right? In which equation? In equation 7, and carrying out the integrated integration, and carrying out the indicated integration. When we do it, the result is, I will write directly, the result is omega d is equal to Vs times 6 pi square n whole raised power 1 by 3. Let me name it as equation 8. Omega d is Vs times 6 pi square small n raised power 1 over 3, where this small n is Na over V, and being the Na being the Avogadro's number of atoms in the solid, because we are taking 1 mole of the solid, V the volume of the sample. So this small Na is what? This concentration of atoms in the solid, right? Omega d by frequency is Vs 6 pi square n raised power 1 over 3. You check it. This is your home assignment, homework 1. Check it. What you have to do? Simple. You have to substitute for G omega into equation 7. G omega is this density of states function. Then you have to solve this integral and check that omega d by frequency is given by equation 8. This is your one homework. So let us move to the total energy. So returning to equation, where is my total name of the equation? This one, 6, 3 total energy of the solid, 3V by 2 pi square Vs cube omega squared h bar omega by e raised power h bar omega by kt minus 1. So returning to equation 6, this was my equation 6. The total energy is now given by the total energy is now given by what is total energy equal to, I will use some other color, 3v by 2 pi square vs cube integral 0 to omega d h bar omega cube over e raised power h bar omega by kt minus 1 d omega. This is my equation 9. Let me encircle it. What is it? 3v by 2 pi square vs cube integral 0 to omega d h bar omega cube by e raised power h bar omega by kt minus 1 d omega. This is simply equation 6 with limits, right? But as we said, we cannot solve this equation 6 for total energy without limits. Limits were decided. 0 is lower limit and upper limit is omega d, d by frequency, right? And the heat capacity CV, which is representing heat capacity per mole at constant volume, which is found by differentiating this equation, that is equation 9, with respect to T, temperature, is, as you know, at the start we said, if we differentiate total energy with respect to temperature, treating volume constant, we get the heat capacity at constant volume for 1 mole of a substance. So this is our total energy, equation 9. So if we differentiate it with respect to temperature T, we will get heat capacity CV, right? And when we do it, we get this expression. CV is equal to 3V by 2 pi square Vs cube h bar square by kt square integral 0 to omega d omega raised power 4 e raised power h bar omega by kt over e raised power h bar omega by kt minus 1 square d omega. Let me name it and encircle it. This is my equation 10. I will check it. Cv is 3v by 2 pi square vs cube h bar square over kt square integral 0 to omega d omega raised power 4 times e raised power h bar omega by kt over e raised power h bar omega by kt minus 1 whole square d omega. How we obtain it? We differentiated equation 9 with respect to temperature. So this is your homework problem 2. Homework 2. Check it. What you have to do? You have to differentiate equation 9 with respect to temperature T. You will get expression for Cv given by equation 10. Right? This is your homework 2. I have given you second homework to solve for omega d by frequency by solving the integral in equation 7. These are your 2 homeworks. So this equation 10 gives us the heat capacity per mole of a substance, per mole of a solid substance at constant volume according to DEBYE model. This is all for today. I stop here. Before stopping, I will just summarize the things. So first we said how we define heat capacity. Then we said how we can obtain heat capacity at constant volume by finding the derivative of total energy with temperature at constant volume. Then we said how the heat capacity of solids depends on temperature. Then we said Dulong-Pettit law says Cv is approximately 3R, so which is true at high temperatures, but at low temperatures Dulong-Pettit law fails. Then we said how Einstein tried to solve this issue. So he did not use the classical result for average energy of an oscillator equal to kT. He took it h bar omega by e raised power h bar omega by kt minus 1. So when this was done, he obtained the expression for Cv given by equation 2. Then we said it in general matches the curve and it predicts Cv approaches 0 as t approaches 0, but the manner in which Cv approaches 0 doesn't match with the experiment. According to Einstein model, Cv approaches 0 exponentially, but experimenters show Cv approaches 0 as dq. Then we said Peter DEBYE solved or tried to solve this issue by considering the collective lattice modes. So using sound waves as a prototype of lattice modes, DEBYE assumed that all these modes have a character similar to sound waves, that is, they obey the same dispersion relation 4, right? Then we used this expression to find the total energy according to Peter DEBYE, where this average energy per oscillator was same as taken by Einstein, but now we use the idea of density of states, which we have already calculated. Then to solve this integral, we needed lower and upper limit. Lower limit was obvious, omega 0. Upper limit was decided by Peter DEBYE using this cutoff procedure, where he said the total number of modes should be equal to total number of degrees of freedom. So this integral g omega d omega 0 to omega d must be 3na. Then from that we defined this d by frequency, and I gave you homework to solve for omega d. Then when we put the limits, we got this total energy expression. Then I gave you another homework to differentiate it with respect to temperature and to obtain this expression 10. So we are here. This is the expression for heat capacity per mole of a solid at constant volume according to Peter DEBYE. So we stop here. We will continue this in next lecture. Prepare your exams. Don't waste your time. Go through all the lectures. Do all homework. And do not forget to like and subscribe my channel. You can comment in the comment box as well. Thank you. God bless you. Assalamu alaikum.